Welcome back. This video is going to be over periodic trends. That kind of goes along with the material that you covered in the POGIL in class. So first, look at atomic size or atomic radius, which is just defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. Another way you can think of the atomic radius, right? If an atom is a sphere, then the radius would just be the distance typically from the nucleus to its outermost electrons. That's one thing to keep in mind. Now, the group trend. As you go down a group, remember this is much like that model 2 from the activity you're doing in class. So as you go down a group, the atomic size will generally increase or increases. For example, if we draw Bohr models for hydrogen, and likewise lithium, and then finally sodium, as you go down a period, the atomic radius is increasing. And the reason for this, right, hydrogen only has 1 energy level, lithium has 2, sodium has 3. So just like in the POGIL activity, each time you jump down a period, you are starting a new energy level or adding an additional one. So as you go down a group, the number of energy levels increases. Means the nucleus, which hopefully you recall has a positive charge, is farther away from the nucleus, is farther from the outermost energy level of the electrons. And this attraction of the positive nucleus and the outermost electrons, which are negative, becomes weaker due to this increased distance. Now, as far as the period trend, atomic size decreases in general as you go across a period from left to right. And if we're looking at these Bohr models again from lithium, beryllium, and boron, now instead of going up and down, we're going left to right. This is lithium. Beryllium. And boron. You got 3 proton nucleus there, 4 and 5. And all of these have the same number of energy levels. So this is just like model 3 in the activity you did in class, where hopefully remember that said if you can understand what is going on between the force of attraction in the nucleus and its outermost electrons, you can basically predict or know the reason for the various trends that we'll be discussing in this class, which is atomic size, which is atomic radius, ionization energy, and electronegativity. So as you go across a period, remember, the force of attraction between the outermost electrons and the nucleus was increasing. And that means these protons in the nucleus are able to pull these electrons closer to themselves because they're being placed in an existing energy level. They're not being placed in a new energy level that is physically further away from the nucleus. Okay. So as you go across the period, the number of energy levels stays the same. The size of the atom, you would think, would not change. However, the number of protons increases in the nucleus, and so it's able to attract those electrons and pull them in more closely. And so that's why you notice that the size of the atom decreases as you go across. So, to put this all together for atomic radius, is that the largest element on the periodic table is going to be in the lower left. And so we just refer that, let's say francium would be, in theory, the largest element. Right? It's radioactive and its half-life is maybe 28 minutes. So it's not, whatever francium gets created is not going to stick around for long enough to do anything with. Closer an element, right, to the lower left, the bigger it will be. And right, if we just want to talk about in general, and I'll just draw a crude periodic table. Atomic radius increases as you go down and increases as you go across. So in general, it kind of goes from small up here to biggest down in this corner. Now let's move on to ionization energy, which ionization energy is defined as how much energy is required to remove an electron from an atom in order to form a positive ion. It's basically how much energy it's going to take to remove one of the outermost electrons. Now, hopefully you can understand that this does require energy in order to do so, because an atom is not going to just willingly give up its electron, or an electron that it has, because there is a force of attraction between the nucleus and the outermost electron. And again, once again, if you can understand what is happening between the force of attraction between the nucleus and its outermost electrons, that will tell you again the trend for ionization energy. Because if the force of attraction is higher when, between a nucleus and its outermost electrons, then it's going to take more energy to remove that electron. It would be the difference of if you are holding on to something very loosely and a friend tries to get it out of your hand, that's going to take less energy or effort on their part as opposed to if you are holding onto it very, very tightly. So, if we're looking at an atom versus an ion. Remember, an ion is just an atom or a group of bonded atoms, if you're talking about polyatomic ions, that have a positive and negative charge, which means the protons and electrons are not present in equal amounts, that there's an imbalance. So the attraction between a positive nucleus and a negative outermost electron increases. So if the attraction, so we're talking again, if the force of attraction between the positive nucleus and the negative electron increases, it is going to be harder to remove the electron from the atom. And so it's going to say it's going to take more energy. And the atom is going to have a higher ionization energy. Basically just saying the greater the force of attraction between the nucleus and its outermost electrons, the more energy it's going to require to remove that electron. Likewise, if the attraction between the positive nucleus and the negative outermost electron is decreasing, it is going to be easier to remove the electron from the atom. Which means it is going to take less energy and the atom will have a lower ionization energy. because the size of the atom decreases. The attraction between the nucleus and the outermost electrons is higher, which means it takes more energy to remove the electron. Oops, sorry. Which means it is harder to remove the electron and takes more energy to do so. Okay, and just like in Model 3, it's because the nuclear charge, right, the charge in the nucleus is increasing as you go across the period. And the electrons are not being placed in new energy levels. It's filling the existing one. So if we just want to summarize the ionization trend, right, the element with the largest ionization energy on the periodic table is going to be helium. And basically, the closer the element is to the upper right corner, which, right, that's where helium is. So this is helium, not helium. The larger ionization energy, and it's going to be harder to remove that outermost. So again, if we just want to kind of look in general, here's our periodic table for ionization energy. So it is going to be the exact opposite. It's going to be the exact opposite of the atomic radius. And it makes sense that it would be that way because as you go closer to helium, that means the force of attraction between the nucleus and its outermost electrons is stronger. And it's going to be harder to remove any of those electrons. Okay, this next one. Ionic radii or size. So we'll discuss this more next unit as well, but a positive ion is called a cation. Not a cation. It's just pronounced cation. And it is formed by the loss or removal of one or more electrons. And these electrons are always going to be the outermost electrons, the highest energy level electrons. Okay, and just an example, lithium. Again, if we are looking at the Bohr model, and we can also look at the electron configuration, right? Lithium is 1s2, 2s1. Lithium is always going to want to lose one electron. And one thing you want to kind of take away from this is if you're looking at a general size between the neutral atom and, right, this is the lithium ion, so it would be lithium plus 1. The lithium ion is always going to be smaller than the lithium atom. Likewise, beryllium, it's got 2 electrons there, 2 electrons here. Its electron configuration is just 1s2, 2s2. Beryllium ion is going to form, and we'll learn more about this next class, or next unit, sorry, is that beryllium is always going to want to lose 2 electrons. And it's always going to lose the outermost. So you can tell from here that the cation is always going to be smaller than the neutral atom that is formed. Whereas a negative ion is called an anion, not an anion, called an anion, and is formed by not the loss but the gain of one or more electrons. So oxygen, let's see, oxygen is 1s2, 2s2, 2p4. So there's first ring. There's a second. 1, 2. Okay, so there's oxygen. 1s2, 2s2, 2p4. So it's got 2 in the first, on the Bohr model, it's got 2 in the first shell, 6 in the second shell. The oxide ion is always going to want to gain two electrons, and you'll learn more about that, why oxygen wants to gain 2 electrons, in the next unit. But it will form a -2 ion. And this ion is always going to be bigger than the neutral atom, much like fluorine. Neutral fluorine has got 1s2, 2s2, 2p6 would be oxygen's electron configuration of the ion that it forms. Fluorine's normal electron configuration, 1s2, 2s2, 2p5. Fluorine is going to always want to gain 1 electron to make the F minus. And this is a little bit exaggerated. You'll end up with a 1s2, 2s2, 2p6 electron configuration. And the size of the anion is always going to be larger. So the cation is always going to be smaller, and the anion is always going to be bigger. And in general, you could say that the radii of the cations increases from left to right, and the radii of the anions in an anion period also increase. Oh, sorry. I thought something seemed a little bit wrong. Electron decreases as the cations. So, for example, lithium, as we saw before, right, the lithium ion is just going to consist of 1s2. Beryllium is also going to have an electron configuration 1s2, but this ion, beryllium, is going to be smaller than the lithium one. And the reason for that is that this has 3 protons in the nucleus to 2 electrons. This has 4 protons in the nucleus to only 2 electrons in the first energy level. So these 4 protons in beryllium were able to pull these things in closer. So that means when you're forming a metal and looking at cations, it's going to get smaller. And likewise, boron would be basically the smallest even compared to beryllium, because the boron +3 ion, right, boron's atomic number is 5. If it loses all 3 of its electrons because the ground state of boron is 1s2, 2s2, 2p1. Well, if it loses those 3 electrons to become boron, now you've got 5 electrons that are just pulling on 2 little electrons, and it's going to be a very small ion. Now, if we take a look at these 3 anions that are in the same period, right? Just if we start looking at this from the standpoint of what their ground state electronegativity is. Sorry, not the ground state, their ground state electron configuration, and see what is happening here. It's like, well, this -3 says that it's gaining 3 electrons. So this electron configuration of the nitrogen ion, or the nitride ion, is going to be 1s2, 2s2, 2p6. The oxygen is going to gain 2 electrons to complete its outer shell. And the fluorine is going to gain 1. That's why this forms a -3 ion, this is a -2, that's a -1. So, what is this going to look like? As you go across, you're adding, again, we're talking about ions here. Negative ion is always going to be bigger than the ground state. Actually, I've got this a little bit messed up. This is supposed to be decrease as well. Because in this case, the nitride ion, with a -3 charge, this is going to be the biggest of these 3 anions. The oxide ion, is going to be a little bit smaller than the nitride ion. And the fluorine is going to be a little bit smaller than the oxygen. However, if you were to compare these 3 ions to their neutral atom counterpart, if we were to compare the nitride ion to the nitrogen, the nitride ion is going to be much bigger. This one's going to be much bigger than the oxygen atom, and the fluoride ion is going to be much bigger than the fluoride atom. But as you go across, each of these is going to get a little bit smaller, because here you've got 8 outermost electrons, but only 7 protons in the nucleus. This has 8 outermost electrons and 6 protons in the nucleus, and this has 8 outermost electrons with, fluorine is 9. So 7, 8, 9 protons. So that is what's driving this change here. And this last thing up here, however, non-metallic ions are going to be always larger than the metallic ions in the same period. Because here they are losing electrons, and so they're getting smaller. Here they're gaining electrons, and they're going to be always bigger than the neutral atom. And the last thing we want to talk about is electronegativity. And this is defined as the ability of an atom in a chemical compound, basically mean when it's bonded to another atom, or is going to bond with another atom, it's the ability to attract electrons from another atom in the compound that's bonded to. And it's basically a measure of how good of a sharer it is. The higher the value for the electronegativity, the more the atom will be able to attract and influence the electrons of another atom. And again, this comes down to understanding, and as I've harped and mentioned many times in the class when you're working on that Pogel activity, it all comes down to what is going on between the force of attraction between the nucleus and its outermost electrons. Because the reason I say that is if an atom has little to a very small amount of force of attraction between its outermost electrons and its nucleus, that means it is going to have a very small electronegativity value, because if it hardly has any force of attraction between its own outermost electrons and the nucleus, well, another atom's outermost electrons are never going to be any closer than its own outermost electrons. Whereas if the force of attraction between the nucleus and its outermost electrons is very high, that means it's also going to have a much greater impact in being able to affect or attract those electrons from another atom. So the group trend and the period trend, right, this is going to track along with the ionization energy, because again, the smaller the atom, the larger the electronegativity is going to be, because the smaller the atom, the more force of attraction between the nucleus and its outermost electrons. Okay, and so what that means is electronegativity decreases as you go down a group, right? This is model 2 from that activity in class, where the period trend, right, is explained by model 3. And the size of the atom increases as you go down the group. And likewise, that is what I was just going to mention. Likewise, you go across a period, electronegativity is going to increase. Again, the force of attraction between the nucleus and its outermost electrons increases as you go across a period. The size of the atom decreases. So it's going to be much easier for the nucleus to attract or interact with the outermost electrons of another atom that it's bonded to. So the element with the highest electronegativity on the periodic table is fluorine. And the closer an element is to the upper right, the larger the electronegativity will be. So if we're just looking at our periodic table, so again, for electronegativity, it generally follows this type of thing. It increases as you go up a group, and it increases as you go across the period. Just keep in mind, yeah, when we're mentioning about electronegativity values, you notice I said fluorine and not helium, because noble gases don't form compounds, and the smaller ones are considered not to have any electronegativity values because they will not interact with anything. They are inert. They are noble, so to speak. On some periodic tables, you may see the larger noble gases having a listed electronegativity value, because they will form an occasional compound with either oxygen or something else, but it's very rare. And that will wrap it up for the Unit 2 notes.